Good morning, everyone. Miss Butler here, and I have a video to help you with your square root curve corrections on the electrochemistry summative. So let's get started with multiple choice. All right, here was the first question on the multiple choice. An electrochemical cell based on the reaction above was construction from zinc and copper half cells. The observed voltage was found to be 1 volt instead of the standard cell potential of 1.10 volts. So what I know is that E cell is lower than E standard cell, which means my reaction must have shifted left, because less electrons traveled on the wire, so that means my reaction must have went this way. So thinking Le Chatelier principle, we're going to look for anything that would shift the reaction to the left. Well, let's look at the first one. The zinc 2+ solution was more concentrated than the copper 2+. So this zinc ion was more concentrated. That is one way for us to get the reaction to shift left. So that's a good option. The solutions in the half cells had different volumes. Well, if they change the volumes mid-experiment, that would change concentrations, but if we measured the concentrations ahead of time, it doesn't really matter what the volume is as long as there's enough liquid or an aqueous solution for the electrodes to sit in. The salt bridge contained KCl as an electrolyte. Well, none of those are part of the reaction, so that wouldn't impact anything. Copper electrode was larger than the zinc electrode. Well, that's a sneaky solid, and that's a sneaky solid. So I don't really care about the sizes of the electrode unless that we don't have enough electrode for it to operate. But being larger or smaller isn't going to make a difference. Picture the demo we did in class. If I just put a bigger piece of metal in, that would not make a difference on the voltage. The zinc 2+ electrolyte was zinc nitrate, while copper 2+ was copper 2 sulfate. That shouldn't make a difference. These are both spectator ions, so really it looks like our best choice is A. That's the only one that will shift us to the left, lowering the E cell. All right, this is a nice question because you have to set up the calculation, but you don't actually have to solve it. So a steady current of 10 amps, and we know 10 amps is the same as 10 coulombs per second, is passed through aluminum. So aluminum is always a +3 ion, so it would gain 3 electrons to make solid aluminum. So we write this half reaction to show how many electrons are used in the process for 15 minutes. Which of the following is the correct expression for calculating the number of grams of aluminum? So I'm going to start with my 15 minutes, and I'm going to go from 15 minutes to seconds. So we just multiply that by 60, so my minutes cancels out. Now if we stopped, we'd be in seconds. So I want to go from seconds to coulomb, and I'm going to use this guy right here because I know 10 coulombs is equal to 1 second. That's what this coulomb per second unit means. So I'm going to put the 1 second on the bottom, 10 coulombs on the top. That way my seconds cancel. Now we want to go from coulombs to moles of electrons, and we know that 96,500 coulombs is 1 mole of electrons. They told me about the coulombs up here. You have this on your formula sheet that it's coulombs per mole of electrons. So again, the coulombs cancel, and we have 1 mole of electrons, but this particular half reaction is not 1 mole of electrons. It has 3. So for every 3 moles of electrons, we will make 1 mole of solid aluminum, and then 1 mole of aluminum has the mass of 27. So if I smoosh all of this together, we are going to multiply across the top 15 minutes times 60 seconds times 10 coulombs times 1 mole of electrons times 1 mole of aluminum times 27 grams. And then divide by what's on bottom. 1 minute times 1 second times 96,500 coulombs times 3 moles of electrons. And the only option that has that particular order with the numbers in all of the correct place is C. All right, we did not like this question. A chemist is working with an electrolytic cell that has lost the markings to indicate which output is positive and which is negative, so they don't know the anode and the cathode. Knowing that the cell uses a pair of platinum electrodes that dip into an aqueous solution of 1 molar BaI2, which of the following would correctly identify the negative terminal, which is the cathode? So we're asking essentially, how can I identify what cell the reduction is happening at? So first of all, it's BaI2. So I have my BaI2, and for an electrolytic cell, we're always breaking into the standard state, so solid barium, and I think iodine's I2 is, let's see, should be a solid at room temperature. Yep, solid. So we got a solid here. Don't quote me on that. It might be a little bit gas. No, it's a solid. My bad. We're good. solid. Okay, anyways, so basically we have this aqueous and we're going into the standard states. So I assign oxidation numbers, -1 for the iodines, and so barium has to be +2. And then because these are the standard states, they go to 0. So barium goes from +2 to 0, that's gaining electrons. Gain electrons is reduction. I goes from -1 to 0, that's losing electrons, that's oxidized. So if we are talking about the cathode, right now we think that the barium is going to be reduced. So we take the barium half reaction, Ba plus 2 is going to gain 2 electrons to make the barium solid. I look at my chart and get the reduction potential for that half reaction as negative 2.9 volts. Here's the kicker. We have an aqueous solution, which means this half reaction competes with water. Water could also be reduced. So here is the reduction half reaction for water. We need to be able to recognize that on a chart. And we know that it has the reduction potential from the chart of negative 0.83 or negative 0.83 volts. So we pick the one that is more positive, which is this guy here. So this is the reaction that is happening at the cathode because it has the more positive potential. So now let's look. We know this is happening. Let's look at the choices. A brown color will appear because I minus turns into I2. Well, that's the oxidation half reaction, so that's not the case. The cathode will lose mass over time. Well, we know big fat red cat, the cathode gains mass. The cathode will cause Ba2 plus to become Ba solid and form a visible solid. Well, if this red half reaction were occurring at the cathode, then that would absolutely be the best choice, but it's not. Water is being reduced. The cathode will cause water to turn into H2 gas and show visible bubbling. Well, look at the product of the reduction, H2 gas, so that is happening, and there's no way to identify the cathode. Well, that's not true because we just did it. So D is our best choice for this one. All right, this one, we had some issues with 4 and 6 mostly. So I have a picture of the solid cadmium electrode, the cadmium 2+, solid silver electrode, and silver plus ions. We also have a balanced equation, which is, I think, the most useful part. I think the picture messed some of us up because we know electrons go, let's get my pen back. Electrons go from the cathode to the anode, right? But here's the issue. I don't really, when we picture, I guess, electrons going from left to right, that does not mean if we increase things over here, the reaction shifts right, or if we increase over here, the reaction shifts left. That is not true because both sides of this cell have reactants and products. Look, solid cadmium is a reactant, cadmium 2+ ions are a product. Solid silver is a product, silver plus ions are a reactant. So it's not looking at the picture and saying, well, this cell goes up so we shift right, or this cell goes up so we shift left. It's all about the balanced equation. So let's look. The silver electrode is made larger. Well, in this equation, silver is a sneaky solid. No sneaky solids. So if I just stick a bigger piece of silver in there, it is not going to make a difference. And so there should be no change in voltage, which is C. Okay, the salt bridge is placed by a platinum wire. Well, we know the salt bridge is going to be something kind of spongy, paper towel-like that is soaked in a positive and negative ion, so usually some sort of a salt with no interference in the reaction. But if I just put a wire there, we're not going to be able to get this to go because we're going to get a buildup of charge. So the voltage will become 0 and stay 0. Most of us got that one. Okay, the concentration of the left beaker. So let's see, the left beaker is the cadmium. So what I'm doing here, let's do green. The cadmium, the left beaker, is increasing. So I am increasing the concentration of cadmium 2+, which is a product. So this left beaker, because it's aqueous cadmium, we are increasing that. So if I increase the concentration of a product, we are going to shift left, which means my voltage is going to decrease. Less electrons are transferring on the wire, so letter A is my best choice. Again, I think it has to do, or we would have been stronger if we looked at this equation instead of just saying, oh, we increase the right, or we increase the left, so more electrons must travel on the wire. And in fact, if I increase the concentration of cadmium, we're actually going to get less electrons on the wire. Or excuse me, cadmium ion, cadmium 2+. All right, I have a balanced redox reaction. How many moles of ClO2 minus are needed to react completely with 20 mils of 2 molar KMnO4? So first of all, I know I have 2 molar, and molarity is equal to moles over liters. So 20 mils is 0.02 liters. So I crisscross multiply. 0.02 times 2 is going to give me 0.04 moles. Again, think of this as mental math-wise, we are doubling what we have here. Double this, we get 0.04. And KMnO4 is the same as MnO4 minus. So that's what we're starting with. We're looking for how much ClO2 there is. So we're going to start by finding X. Remember, this is multiple choice, so in terms of showing your work, you don't have to show any work, so I'm not going to set up a whole BCA table for everything I don't care about, right? That would be a waste of time. I'm just focusing on the 2 columns I need. So here's what I know. Because they said react completely, both of these are going to run out. So I can say to find x, 0.040 minus 4x equals 0. So 0.040 equals 4x. We divide both sides by 4. Mental math. We're taking 0.04 divided by 4. X is going to be 0.01. So that's my x. And so now all we're going to do is plug in minus 3 times 0.01. So let's find my question mark. Question mark minus 3 times 0.01 equals 0. Well, question mark minus 0.03 equals 0. We add that to the other side, so we must have 0.03 moles, which is option A. All right, so which of the following best accounts for the fact that this reaction generates electricity? When I say generates electricity, you can think of it as multiple ways. You could think of it as thermodynamically favorable, so delta G is negative. You can think of it as the E cell is a positive value. We're getting a voltage. So here's what I did first. I assigned oxidation numbers. So we have normal chlorine gas, so that's 0. This is an ion, so -1. This is an ion, -1. And this is standard state of I2, so it's 0. So I can see chlorine goes from 0 to -1, which means it's gaining electrons, which it's reduced in this reaction, and I is going from -1 to 0, so it lost electrons, it's oxidized. So these things, as they are happening, is thermodynamically favorable. Well, Cl2 can easily lose 2 electrons. No, it's gaining electrons, so that's not a good choice. Cl2 is a stronger oxidizing agent. Well, if Cl2 is, or chlorine's being reduced, that means Cl2 is an oxidizing agent. So basically what we're saying is this is better at being an oxidizing agent than this guy would be, because if we reversed what was oxidized and what was reduced, remember the reaction would be reversed. So that seems like a plausible choice. I atoms have more electrons than do atoms of chlorine, so we've never talked about number of electrons being an influencer. I minus is more stable than I2. Well, no, because we are making more of this. Both of them exist. We are producing more of this, so stability is not an issue. And more soluble, we don't care really anything about solubility when we talk about these galvanic cells. So it seems like B is the best choice. All right, hopefully that helped with your multiple choice. If I skipped over any problems you got wrong and you cannot figure it out on your own, please let me know during office hours and I can help you out. Let's look at FRQ. All right, here's the first one. An electrochemical cell is constructed with an open switch as shown in the diagram. So here's the switch. When it is closed, a strip of Sn and a strip of unknown metal X are used as electrodes. When the switch is closed, the mass of the Sn electrode increases. This is huge. The half reactions are as follows. So the first question, label the cathode and justify. First of all, you can label it on here, okay, or you could have said the left one with the Sn, but some students did not justify. So couple of things, looking at these and telling me that this is more positive, so it's reduction at the cathode, is not a good choice because we don't know what the voltage is. Here's a great answer that Tanner wrote. Sn is the cathode. When the switch is closed, the Sn gains mass, which means electrons must be flowing towards that electrode, joining the aqueous Sn2+, to form solid Sn. So essentially he's saying the electrons are going this way, and when they join, the Sn2 plus in the solution joins, and so we gain mass at the cathode. Great answer, Tanner. So that's a good justification. Okay, draw an arrow to indicate the direction of the electron flow. We know that electrons go from the anode to the cathode, so your electrons are actually going from the right to the left. If you got this part wrong, but you drew the electrons correctly for what you said incorrectly up here, you did earn the points. But on your corrections, if you got A wrong, I really want you to fix the majority of your problem because it does change a lot. So if you missed A, I need you to fix pretty much everything in this problem. Okay, so go back and do that even if you got the points because, again, I was being nice and giving you the points based off your wrong answer for A. Okay, if the standard cell potential, so the overall voltage is 0.6, what is the reduction potential here? So we know that our E cell is going to be the reduction at the cathode minus the reduction at the anode. I got distracted. Sorry, back to this one here. Make sure it's obvious that your electrons are traveling along the wire. I had some of you like with electrons up in here. That to me looks like the electrons are moving through the air. We don't want electrons through the air. So just make it super obvious that you know they go on the wire. They don't go on the salt bridge. They only go across the wire. Okay, back to letter C. So we're going to take the reduction at the cathode minus reduction at the anode. And so it's going to overall equal 0.6. And we know that the cathode is 0.14 minus X. So what we can do is we can add over this 0.14. So we get negative X equals 0.74, and we divide both sides by -1, so X equals negative 0.74, and the unit is volts. You did lose a point if you did not have a unit. Okay, identify metal X. So this is where we can look at our standard reduction potential chart, and we find the half reaction that has the reduction potential closest to negative 0.74, and we want to identify the metal. Don't just give me the half reaction. We want the full metal, and so the metal would be chromium solid. Write the balanced net ionic equation. So now most of us, if we got this far, we were good because we knew this was Cr3 plus 3 electrons makes Cr solid. We can flip this guy because it's the oxidation, and we can easily balance by multiplying this one by 3 and multiplying this one by 2 once it's reversed. Okay? And then lastly, if the concentration of the Sn2 plus is changed from 1 to 0.5, will the cell potential be greater, less than, or equal? So you had two options for this question. You could have either used the Nernst equation that the standard E cell, the E cell that we're calculating is equal to the standard E cell minus 0.0591 over the number of electrons times the log of Q, which we can use our balanced reaction for. So calculating that new E cell, you should have gotten 0.591, which shows that the new E cell is less than the standard. And then again, you're showing your work plugging in, so that is an option. Or you can use Le Chatelier principle. If you look at the balanced equation that you got in letter E, it should have been 2 Cr solid plus 3 Sn2 plus makes 2 Cr3 plus 3 Sn solid. And if I'm lowering the concentration of this, we're going to shift to the left to overcompensate for that. So because it shifts left, that means the E cell will be less than the standard, less electrons on the wire. So either option, you did not need to do both, either Le Chatelier, but I'm looking for lowering the concentration of a reactant, shifts the reaction left. Due to Le Chatelier, less electrons on the wire means lower E cell than the standard. Or plugging and chugging and solving it out for me. All right, this one is exactly like our lab, guys. This is pretty like word for word what our lab was. So we have to balance a redox reaction as the first part before we can do the calculations from our lab. So I assigned oxidation numbers. I figured out that iron loses electrons, so it's oxidized. Chromium gains electrons, so it's reduced. Here's what killed some of us. We always balance the non-oxygen and hydrogen first. There are 2 chromiums. I need a 2 here. That is important because it changes the charge. So then what I can do is I can add my 7 H2Os, and I can add my 14 H pluses. And when we add up the charges on this side, I have 14 positive and 2 negatives, so I have a positive 12. On this side, I have 2 of these 3 pluses, so I have a plus 6. So I only need 6 electrons on this side. I need 1 electron on this side, so then all we're doing is multiplying this reaction by 6, and we can smoosh and cancel out those electrons. Once we have the balanced equation, we can use the concentration of the Cr2O7 and the volume, here's the molarity, there's the volumes, to find moles, and we can do a BCA table to solve for our question mark. Once I know the question mark of Fe2+, we can turn that moles of Fe2+ into grams and divide the grams by the grams of the sample. Most of us did pretty well with letter B, but if you struggled with it, look at your lab, and if you're still struggling, come on into office hours, let me help you out.